global demand for energy and water continues to grow, while traditional cooling systems consume large amounts of electricity and generate significant greenhouse gas emissions. Radiative cooling is a sustainable alternative that allows objects to release heat directly into outer space. The atmosphere has a transmission window at wavelengths between 8 and 13 micrometers through which heat can escape. Thanks to this phenomenon, any surface facing the sky can be passively cooled without consuming energy. Radiative cooling has been used since ancient times, when ice was produced in the desert of ancient Persia even under warm ambient temperatures. In the 1960s, this technology began to be systematically studied with the introduction of materials such as plastics or silicon oxide for nighttime radiative cooling. The main challenge is achieving daytime radiative cooling. This challenge is complex, as it requires materials with high emissivity in the atmospheric window, 8 to 13 micrometers, while also exhibiting low absorption in the solar spectrum, 0.3 to 2.5 micrometers. A daytime radiative cooling material is a special type of surface capable of remaining cool even under direct sunlight. This is achieved by reflecting near-infrared incoming solar radiation while simultaneously emitting its own thermal radiation efficiently toward space through the atmospheric transparency window. Thanks to this combination, the material can lower its temperature without energy consumption, relying solely on the laws of physics. The Opera project aims to improve radiative cooling by 20% using advanced optical designs. To this end, concentrators based on non-imaging optics are developed to better direct thermal radiation toward the sky. These devices must emit within the atmospheric window, 8 to 13 micrometers, and reflect the rest of the solar spectrum. Beyond cooling surfaces, Opera also focuses on adapting optical systems to tubular structures in order to cool fluids. Specific optical systems have been designed and fabricated for both daytime and nighttime operation, adapting their geometry to different orientations and tilt angles ranging from 0 to 30 degrees. The objective is to understand how solar position, atmospheric transparency, and zenith angle influence the ability to transfer heat to outer space. This result is crucial because it shows that CPCs multiply heat rejection capability by acting as optical concentrators that better direct radiation toward the sky. Furthermore, their performance shows little dependence on orientation, facilitating integration into real-world applications. Experiments conducted within the Opera project demonstrate that combining radiative cooling materials with advanced optical designs can increase cooling performance by up to 3 times compared to using a radiative cooling surface alone. Even under direct sunlight, cooling tests were also performed on a fluid circulating through a tube using a thermal solar concentration system configured to operate in reverse mode, extracting heat from the fluid and releasing it into outer space. In this case, the use of the radiative cooling material reduces the temperature of the circulating liquid by half, and combining the radiative cooling material with the CPC reduces the temperature difference to nearly 0. To validate the usefulness of radiative cooling in IoT devices powered by ambient energy, tests were carried out using 2 technologies: photovoltaic modules and thermoelectric generators. The use of radiative cooling material reduced the temperature of the photovoltaic module by approximately 2 degrees Celsius, resulting in a 1.1% increase in electrical conversion efficiency. Although this may seem modest, it is significant for IoT systems where every milliwatt counts. In Peltier-type thermoelectric generators, the radiative cooling material enabled a 20% increase in generated voltage due to the larger thermal gradient between its surfaces. When the CPC structure was added, the temperature reduction reached up to 2.5 degrees Celsius, depending on solar position and system orientation. This confirms that CPCs can intensify radiative cooling even under variable lighting conditions. Measurements performed on luminaires showed temperature reductions between 7 and 14 degrees Celsius, depending on the arrangement of the radiative cooling materials. These experiments open new application fields for improving performance of photovoltaic generation systems and lighting systems that must operate during daytime. Examples include road signals, aeronautical and maritime beacons, outdoor industrial lighting, agricultural lighting, event lighting, as well as solar-powered luminaires and signage. In general, these are lighting applications that require continuous visibility, even under sunlight, for safety, operational, or permanent signaling purposes. Other applications of radiative cooling materials include their use in roof coatings or radiative cooling fabrics for awnings and shading elements.